down to 1/10. So that's all computed in the spreadsheet. These are very easy spreadsheets to build. So let's just go back here for a second to where we were. And so that's what's happening here. This is taking the last value, the derivative, multiplying it by my dx, and then I take that value and I add it to the last value. So I take the value of my last number, add the differential, and I get my new estimate. And that just spreads all the way down. So it's a very easy thing to do, and you can do these with normal spreadsheets. After a while, your students will be convinced that this is, in fact, making the estimate. Now, the important thing, yeah.
How's your f of x at 2 now? How good did you do?
I'm at 5.6.
That's where it is?
Yeah.
Oh, that didn't change? You didn't change that?
No, he went back to 10.
I went back to 10.
Oh, okay.
Yeah, if I change it to, okay, that's a good thing, because students like to do that. So let's change it to 20. And now I have to go a little bit further to get my estimate.
Where's our x?
Let's go down.
Here's 2 now, that's 5.8.
So then clearly 40 would give us 6.
Right. Okay. So that's really nice. And what we're interested in is if you change the initial value, okay? So what happens if you change the initial value? Let's make that 3. Is that the right spot there? So let's change this to 3. Why is it doing that? Oh, because I got some crazy stuff here. Let's do this and get back to it. There we go. Okay. I was in a cell. So I'm going to change this value to 3. Oh, I know why it's doing that. Because I was pushing the button. There we go, this 3. All right, so here's 3. You see everything changes, all right? So the initial value is 3, so everything's going up. It's going up by the same amount because the differential equation here doesn't depend on the y, it just depends on the x. You can do interesting things if the derivative depends both on the x and y, but because we leave that pretty quickly and go to focus on this, then it's a lot easier. Because when it depends just on x, I can compute the derivative without even knowing what the initial value is. Because the derivative just depends on x, so I can do this column without even knowing what's going on for my initial condition. And I can compute the differentials without even knowing what's going on with the thing. So then I'm just adding these things on. And this thing here, if I start at 3, well, I'm just going to add from 3 and keep adding on. So what we observe is that what's really interesting here is that the net change between where you start and where you finish is basically kept track of by the last column. The sum of the differentials, which are coming from the derivative times the dx. So if we want to figure out what the net change is, an estimate of the net change is coming from adding up the stuff in this far right column and adding up the differentials, right? The things that are the derivative of the function times dx. So that's our differential, and that's, if you've been doing differentials earlier, that's what the differential is. It's the derivative times dx, that's what dy is. So we're just adding up all the dy's. We're getting an estimate for the change in the y's. And this is the way actually Leibniz thought about it. We're adding up the changes in the y's. We think about that as motion. We're seeing this change in position. And in the end, we get our estimate for our net change in position. So if we use this as the motivation for what we're eventually going to call the definite integral, the definite integral is going to come from multiplying a function times a change in x and then adding them up and seeing what happens when we make the change in x small. Will those sums get closer and closer to one particular number? All right, so the motivation is coming from differential equations, making estimates, and seeing what happens when we make things small, and it's tied to a model of motion and net change in position. Okay? So you use that for your model. Now, there are other models that can work the same way. For example, if you want to do economics, maybe you'd like to do economic modeling in your class. So you've talked about marginal costs. You've talked about marginal profits. So if you know your marginal costs for a short change in whatever's controlling your profits, maybe it's your price. Right? Your price controls your sales control your profits. So you're changing the price, small change in price, small change in price and you somehow you add up your, or maybe it's the units of production. All right? So you have units of production times the price. You've got, because those are related to each other, so it could be the productions related to the price, smaller change in price, related to change in production. You look at the marginal change, that tells you how much for a small change in price, and pretty soon you're saying, well, what would be the net change in my profit if I change my price from here to here? Because the profit is going to be determined by marginal times change in amount. All right, so those margins are the derivatives. So you're taking those and you're adding up and get the net change in profit, get the net change in cost. So you can take this and interpret these sums in that model as well. Now you want a way to visualize it. Well, the value of the derivative, here's the derivatives here, and traditionally what people do is they look at that's our derivative, this graph there, and they look at areas. But what areas? Why would you ever look at areas first? Well, the reason you look at areas is because you're multiplying a value times another, times a small change. But you can visualize this with the mapping diagrams, and I have a mapping diagram over here. This is how the change is happening in a mapping diagram. This is our position, and I'm going here. So these are the x's, and those are the y's. And I say, how did you do that so easily? Well, it's actually very easy. So this is the top secret revelation for the day. This is what, if you get anything out of my talk, it's this trick, okay? So that's a mapping diagram. Everyone agree that that looks like a mapping diagram. You've got my inputs here, and my outputs there, they're pretty close to the thing at the 4.9 in this estimate. Okay. So that's a mapping diagram. How did I get that mapping diagram? Well, it's really quite nice. Here's what you do. This is the function, and it's starting at 3, so that's why it means. That's why I went to 4.9, I only went to 1, okay? So, how do I get that mapping diagram? Well, here's what I do. You highlight 2 pieces of data. Now, we know how to, I hope you know how to get a graph of that with a spreadsheet. There's a chart feature. This is an old one. And you use a scatter chart. So you go for scatter, and then you choose, and maybe I'll use the ones that's kind of straight. So that's going to put a scatter plot. Here's what it looks like. Like a curve. That's how the graph of the function is actually looking from the data that I have. Okay? But so I'm going to go to the next feature and show you how to get a mapping diagram. So you go next. There's the curve, and it says I'm choosing columns because there are 2 columns, right? All right. So if I want to get a mapping diagram, all I have to do is change that to rows. That's a mapping diagram. So this is a really very easy way. If you want to talk about functions and do mapping diagrams in any way at all you have to do is make sure you label the tops of the columns, because that plays a little bit into the way that the spreadsheets do it. All you have to do is put your data in the 2 columns. You want a graph? Fine, use the column. You want to do a mapping diagram? Just switch it to rows, and you got a mapping diagram. You can drop this out. You've got a nice mapping diagram. You put the data in. It'll show that as well. That's how I got the mapping diagrams. For this. Okay. So that's your bonus for the day. Everyone happy with that? You can use that everywhere. Because I know you guys don't teach calculus all the time. You teach beginning algebra, you teach intermediate algebra, you teach elementary functions. That's your bread and butter. All right. When you start teaching functions, you can now not only can draw a graph, you can draw a mapping diagram, which helps with a lot of concepts, like trying to explain graphically what composition is like. Yeah. All right. But mapping diagrams, way to go.
Or inverse image.
Or inverse image, yeah. These are just direct and very transparent. Well, they're transparent. Okay, so that's the Euler's method. And it takes us to the way to deal with the definition of the definite integral. All right? So, the motivation for defining the definite integral comes from estimating the solution to the initial value problem. Visually and numerically estimate with graphs, and I did have a graph of the function, but more important, the mapping diagrams. Because the mapping diagrams are going to tell us that if we do better and better estimates, we're going to get closer and closer to the net change position. If we can find a position function, then the sums that we're getting in that last column are going to be getting closer and closer to the net change of position. So all we have to know and believe is that those sums, as we make the n larger for our Euler method, or make the dx, or the delta x, smaller, this is getting closer and closer to one particular number, which is the net change. So from that, then you can move to try to define the definite integral. And you can also connect it because you are doing, you say, well, how else do you take things and multiply them? Well, you multiply velocity times change in time gives us change in position, marginal cost times change in amount produced gives us net gives us costs, revenues the same way. Well, a simple one in geometry, base times height is the area of a rectangle. All right, so we put the dx's in the rectangles from 2 to domain, and you build little rectangles right over them. And when you do that, when you build the rectangles right over them, the height of those rectangles are d, and you do more than one of them, it's going to fill in and make it look just like the graph of p. And the rectangle is going to look just like the area under the curve, and so you've got that connection to the area under the curve, that's the velocity function. You've got that connected, and that's the way that Galileo connected to solve his velocity problems. He was looking at area under the curve. All right? So you really are connecting with the interpretation of differential equations, estimation, and modeling all together. When you get that fundamental theorem of calculus, it's because you define the definite integral connected to an estimation that made sense and was a problem-solving estimation, the same way that finding instantaneous velocity and finding slopes of tangent line was a problem-solving estimation that gave you the derivative. So the concept of the definite integral comes from estimations, consolidating those estimations, and then after you've done that, then you can move on and say, well, we're using, in doing this, we're always using the starting point. So we're using, if you think about this as an interval in the geometry, it's the left-hand endpoint of the interval. What if we used a different point to estimate the velocity? Well, that's just looking at a different derivative at some other point in the time of the interval and using that. So you can use right-hand endpoints, left-hand endpoints, midpoints. You can choose any point you like in the interval. You're getting close to Riemann sums, except for the fact that you're still breaking things up into equal pieces. So you're still doing the Euler area of the sums. If you start to say, well, I don't care about the size of the rectangle. Some rectangles I don't want to waste my time on because the function's not changing very much there. Other intervals, the function's changing a lot. So I want to be able to focus on where things are really changing a lot. So I don't want to use the same thing all the time. I can miss a lot of things. You can get real problems if you're always using rational numbers for your evaluations, like the Dirichlet function, which is 0, 1 as rationals and irrationals. You get all kinds of contradictions by using that kind of thing. So you need to be able to think about Riemann sums, but the general point choice of the Riemann sum in the interval is enough to get you the generality. All the functions you're ever going to deal with in Calc 1 pretty much are continuous. So they're all going to have it. So whichever definition you want to use, they're all going to have the same ability to estimate. So you can get to the Riemann sum. You can use upper and lower. Some people still remember what upper and lower sums were like in the calc courses. That's the way I learned it, upper and lower sums. You had the up, and I had a friend in graduate school, and he taught upper and lower sums at that time to our students, and he told the students, this is really interesting because there were two twin brothers. Their German names, I can't tell you, but they translate to upper Riemann and lower Riemann. And these brothers had these two sons. Okay, so here's, I think I have a connection here. When am I supposed to finish? At 10 after?
10 after, yeah.
Okay, I got 5 minutes left. So I'll take you through, I think this is close to the end of the slides here. There we go. So there are two objectives in this fundamental theorem of calculus. Estimate net change in distance from the differential equations using Euler's method, and measure the error. Now I haven't talked about measuring the error, but if you're doing a function that's monotonic, so if the derivative is monotonic, all right, then if you're using the left, if it's monotonic increasing, and using the left-hand endpoints, it's always going to underestimate the distance you've traveled. All right? So if you can find the net, you can estimate what the error can be from that velocity estimation, because at one end you're going too slow, at the other end you're going too fast, so you can estimate what the possible error could be from that choice. and you can use that to make an error on the estimate change from the interpretation of differential equations. Okay, and that goes back to actually to Aristotle, who was actually he wrote something about running people running, and he had this clever thing. He said, "The person who runs fast will get there first." And will travel more distance in the same time. What a clever guy. Okay. Aristotle said that. He knew all about derivatives. So the key ideas here are, again, the idea of when x is closed, f of x is approximately equal to a linear function, that's the linear estimator, or you can use the mean value theorem approach as well and see that the derivative at some point in time will actually tell you what the difference is, which are also two different ways to justify the fundamental theorem of calculus in a more quote, rigorous fashion by telescoping sense with the mean value theorem. So with this reorganization, the treatment of the fundamental theorem of calculus forms a sensible part of the whole first year program in a thematic approach to understanding the mathematical themes that run throughout the course and can be used later on in starting to deal with series of, not with just, well, let's deal with some sequences and how they converge and eventually get to talking about Taylor's theorem, but starting off by thinking about a differential equation, like let's think about a polynomial that would match the exponential for a differential equation up to degree n. A polynomial whose value at 0 is 1, and its derivative at 0 is 1, and its second derivative at 0 is 1, and its nth derivative at 0 is 1, just matches the exponential, but it stops because it's a polynomial, eventually it's 0. Right? What polynomial would do that? And then, how can you use that polynomial to estimate? Because you've got a lot of information at one point. How much does that control the estimates of the function close by? We use the Taylor theorem for e to the x first, but then in general, the Maclaurin's theorem, and then the general Taylor theorem, to estimate the value of the function. And then when you do that, you've got an error term right away with the remainder, whichever you use, the integral of derivative remainder, quotient remainder. And from that, you can start talking about, well, so this, for a particular number, I'm getting closer and closer. Then you can start talking about sequences of numbers. And in fact, you won't have all the problems you have early, because when you look at 1 plus 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, you say, well, what is that sequence getting close to? You know the answer already. Because that's coming from the Taylor polynomial for e to the x, and it's got to be getting close to the solution, which is e to the 1, so that's got to be getting close to 1. So you don't have to think hard about that, you just have to make sense out of what you were doing. You have to make sense out of what you're doing, and you can do that early in the course. You want to do an integral. This is one of my favorites. The integral, very hard integral of e to the minus x squared from 0 to 1. All right? That's a hard integral. There's no easy antiderivative for that. Okay? Or put a minus in there if you like. Or I have a minus, e to the minus x squared. So it's a very important integral. It's related to probability. A lot of modeling built off of that. How do you estimate that integral? Well, you do not use midpoint formula. And you don't use Simpson's rule. You take a Taylor polynomial and you don't have to go very far. About 3 terms for the exponential will give you a 6th-degree polynomial when you put in minus x, e to the minus x, when you put in minus x squared. You integrate that term by term. You've got you've got 3 or 4 decimal places estimate without very much computation at all. And what else can you get as a payoff? You've got an error term from the Taylor theorem, which you can use to say how close your estimate is for the definite integral based on the series, based on the Taylor series, based on the Taylor polynomial, based on differential equation approach to the problem. Estimation on differential equation. Well, I hope I've made sense out of the fundamental theorem of calculus for you in a different way. And hopefully, if you're interested, you can find out more about it. If you have questions, you can email me. And here's a link to the sensible calculus. If you have a question, I can show you that some of the web page for the sensible calculus. That's a long. Actually, the easiest way to do it is Google my name and sensible calculus. Yeah. Flashman's easy to remember. Sensible calculus. you'll get a link to the basic page about the project, and some of the sections are available there. The chapter on Euler's method and solving differential equations before you get the integration is pretty complete. The other sections are not up there online. Those are the ones I use most frequently in my classes. Thanks very much. Questions? I guess I answered. Thank you very much. Have any questions?